So myself, Dr. Santhosh Singh, working as an associate professor in Department of Physics, Institute of Aeronautical Engineering. Today, I will discuss about the density of state for semiconducting material. So it will comes under the broad topic optoelectronic properties of semiconductor material. So let's start. So what is the density of state? So density, you know that density means something per unit volume. Okay. So the word density always refers something per unit volume. So in this course of study means the optoelectronic properties of semiconductor material. Once you plot the energy band structure of any semiconductor materials, then available energy of electrons or available energy per unit energy range for per unit volume of electron is considered as a density of states. So the word density gives us an idea that it must be something related to the per unit volume, whereas state refers to an allowed solution which satisfies the boundary condition. It is the general definition of state, which is an eigen solution or mode. So generally for getting the energy band structure, what is the energy band structure? It is nothing but dense energy levels, which comes from numbers of atoms. Okay, why? Because any solid comprises with number of atoms, and each atoms have their different energy levels, and because there are number of atoms, so accumulatively these energy state will create the band. Okay, once we take collectively all the energy level, these energy levels are considered as a band. Okay, so how many these energy levels available per unit energy range for per unit volume of the crystallic structure, means in per unit volume how many number of atoms are present, and for those atoms the energy levels you have to only consider. Then how many energy levels for those atoms are available per unit energy range. Okay, that is considered as density of state. Okay, so density of state will generally denoted by rho k. Sometimes it is also denoted by rho e. Why rho k? Because it always comes from the energy band structure, and energy band structure is nothing but EK diagram. You have to take the K axis and E axis, and you have to plot the energy values between E and K, means at different K points what are the available energy values. So you will get a structure like that. Okay, so this part is considered as valence band, this part considered as a conduction band. Okay, and obviously there are some gap. That gap is refer as energy band gap, EG. Okay, so see here, these energy state are also depends on K vector, also depends on E energy value. That's why density of state can be denoted by in term of E, or as a function of E, or as a function of K. But general notation is rho K. So the density of state in semiconductor is denoted by rho K. This is in the K space, where rho K is defined as the density of state in semiconductor is denoted by rho K, and this is in the K space, and rho K is defined as rho K dk. Means density of state is defined as rho k dk. Means available energy state, available states in per unit range or in dk range. Okay, which is the number of state between k and k plus dk. K and k plus dk. So once you take the difference between this point k to k plus dk point, what you will get? Dk. Okay, means k plus dk minus k, what you will get? Dk. So in the energy range of dk or in the difference of dk k points, how many states are available? That is considered as a density of state. Why? Because these states will only govern the band structure of any material or any semiconductor material. So the density of a state in semiconductor is denoted by generally rho k. This is in the k space notation. So rho k is defined as rho k dk, which is the number of available states between this k point and between k plus dk point per unit volume of the material. Similarly, you can also define on the same way. Why? Because you are defining the density of state for band structure, and in the band structure there are two axes, k axis and e axis. If you are defining the density of state on the basis of this k axis, means you are traveling like in this direction. This is normal ek diagram. So suppose this is k point, this is k plus dk point. So how many available states are in k axis, on k axis are available? How many k states are available on k axis between k to k plus dk is known as density of state and denoted by rho k. Okay, then corresponding each k also you will get some energy value. Means suppose corresponding this k, the energy value is E. Corresponding this k plus dk, the energy value is E plus D. So how many energy states are available between this k to k plus dk point? Okay, or between E to E plus DE energy state. How many available energy states? Allowed solution, in other terms, eigen solution are available between E to E plus DE is also referred as density of state, and it is denoted by rho E if you are considering the energy axis. If you want to tell the energy states or density of state on the basis of energy, then it will be denoted by rho E. But the general notation is rho K. Okay. So if you are plotting or if you are describing the density of state on the basis of K, you should use this notation. And if you want to tell the energy of state on the basis of energy value, you should use this notation. So it is nothing but allowed energy solution or allowed eigenfunction for any particle which are bound, which are not, you cannot consider as a free particle. It will be bound by some boundary condition. So again, what are these E and K? So E and K is nothing but axis. E, K axis, EK diagram, where E is considered as an energy axis and K is considered as K space vector, K vector. Okay. So generally all the plot is considered as a EK diagram, energy versus K plot. Okay. So E and K is nothing but energy, allowed energy solution along with allowed wave vector. Okay. K is nothing but wave vector, K space vector. All these terms will be used for describing the density of state or uh, getting the actual expression of density of state. So, band structure of EK diagram, with the help of band structure of EK diagram, you are able to know what is E and K. So, EK diagram, for every given value of K, there is corresponding E value. Okay. EK diagram is nothing but a band structure plot. So, the ideal plot is like that. Okay. So, the next term, what is written, EK diagram, for every given value of K, there is corresponding value of E. Means for each value of K, definitely there is some energy value. Suppose this is the K1. So corresponding K1, you will get some E1. Okay. So therefore, if I have K plus dk range, I already discussed this. If I have K plus dk range, so corresponding you will get E plus dE range. Okay. So K plus dk will be automatically mapped on E plus dE, because corresponding to each value of K, definitely there will be corresponding E value. That's why EK diagram, and it is nothing but band structure plot. Okay. So therefore, if I have K plus dk, then correspondingly I have E plus dE. So the number of states or points in the EK diagram between K and K plus dk is the same as the number of points between E and E plus dE. So obviously this density of state rho K is always equal to rho E. Okay, means there is no difference between density of state if you are considering either K axis or on the basis of K axis, or if you want to describe the density of state on the basis of energy axis. There is no difference as such difference in term of number. Okay, in term of value for density of state, means from the both way you will get the nearly or exactly same value. Okay. So what is the actual number? What the number of state which are available between K to K plus dk? That is the question. How many states, how many allowed solution for any quantum mechanical body or quantum mechanical particle can exist or exist between the K to K plus dk? Okay. So to know the answer of this question, we have to recall some point about EK diagram. EK diagram I already covered. If you want, you can go to my some previous video lecture, and it is already with the name of EK diagram, exact, where I discussed many things about EK diagram. So, but a quick recall I want to give again, because here it is very important, the all the term which is related to EK diagram, like what is the effective mass, okay, what is the parabolic approximation of band structure. With the help of all these things, we will calculate the exact number of density of state available between this range K to K plus dk. So valence band, so take just a quick review over EK diagram. So valence band and conduction band corresponding to top and bottom part of EK plot with energy value EV and EC respectively. There is a band gap between them. Means what he want to try is to say, if you plot the EK diagram, so this is the ideal diagram. Okay. So the lowest part of this is what? This is your conduction band. This is your valence band. So the lowest energy in the conduction band will be referred as EC, and the topmost energy in the balance band will be referred as a EV. Okay, and obviously there is some band gap. There is some gap between the top of the balance band and the bottom of the conduction band, or minima of conduction band and top of the balance band, and that gap is always referred as a energy band gap, represented by Eg. Okay, so this is some recall about TK diagram. So we have seen that normally the typical number of electron. So why you are plotting the CK diagram? Actually, you want to get the desired solution, desired eigenfunction associated with the free electron, and that eigenfunction or eigenvalue comes as a energy solution, and that energy solution will give the band structure. These are either energy values or energy solution or allowed eigenfunction for all the available electron inside the material. Okay, so we have seen that normally the typical number of electrons in the valence band is of the same order of the number of atoms. So in my previous lecture I already calculated this thing, means how many number of available electrons inside the any material. So it is actually available electrons means the electrons which are nearly free are able to move inside the crystal. So its number is in same order of the available number of atoms. Means if the available number of atoms are around 10 to the power 15. So available number of nearly free electron order, not exactly, I am saying roughly number, is around the same, means 10 to the power 15. So it is already calculated. Okay, if you want to see, you can refer my previous video lecture. So we have seen that normally the typical number of electrons in the valence band is of the same order of number of atoms available inside the solid, which as you have calculated in earlier lecture. So it is how much? It is around 10 to the power 22 per centimeter cube. 10 to the power 22 electrons are available in valence band. Okay, in valence band means total number of electron. Where is the valence band? This is your valence band. This is your conduction band. Means how many electrons are available? 10 to the power 22, nearly. And how it will come? It will comes due to some approximation and some calculation, where basically it depends on how many atoms are available inside any semiconducting solid. Okay, so the same number of electrons are also available inside the solid, but all these electrons are not free to conduct. Which electron will free to conduct? Those electron will only conduct, those electron can conduct which are able to reach anyhow in conduction band. Okay, those electrons are only able to conduct, not all 10 to the power 22 electrons. So obviously all the electrons are not able to reach the conduction band. Okay, so the conduction band electrons number means the electrons which are able to conduct or which are able to move inside the material, their numbers are little bit less comparison to this number 10 to the power 22 centimeter per cube numbers. Okay, so for example, the carrier concentration denoted by Ni of intrinsic silicon. Silicon is a kind of semiconductor. Intrinsic means undoped case. I am considering the undoped case. At room temperature is of the order of 10 to the power 10 per centimeter cube. Carrier concentration. Here the word, the carrier. Carrier means those electrons which are nearly able to do the motion. Means you can consider that electron as a free electron or free charge carrier. Means due to that electron only any kind of electricity will conduct inside the material. That's why the carrier concentration, carrier word is used. Okay, here the total number of electron. We have seen that normally the number of electron, not the carrier word is used. But here, see, for example, the carrier concentration means those electrons which are able to move, which are nearly free, or anyhow those electrons which are available in conduction band. Okay, is how much? Around 10 to the power 10 per centimeter cube. Means very less than 10 to the power 22. Okay, number. So if you dope the semiconductor to make any device, say suppose you want to make any PN junction device, the typical doping concentration could be anywhere from 10 to the power 12 to 10 to the power 70. Okay, which means the number of carriers which are available of this order is how much? Around, means less than this number. Okay, always. Okay, suppose initially carrier concentration means those electrons which are nearly free and able to conduct is around 10 to the power 10. Suppose you want to make any PN junction device, or for suppose you want to use this silicon for device applications, what you have to do, you have to dope some so that it will perform better. So even after doping, the carrier concentration reach up to around 10 to the power 15 per centimeter cube. And this number is even very less than this number. Very less. Initially 10, 100, 1000, there is no such very huge difference. 10,000, then million, then 1 million or 10 million. Then again if you are adding next zero, it will convert to billion. So transforming from million to billion, there is a huge difference. Then once you are adding one next zero, there are a lot of difference, huge difference. So don't be considered as this difference 10 to the power 15 to 10 to the power 22 difference is a small difference. It is very huge difference, numerous difference. Okay, initially this difference 10 to 100, 100 to 1000, you can't consider this is too much big difference. But once you range into billion or trillion region, once you reach to billion or trillion region, it will, every single zero will create the huge difference in availability of free carrier concentration. Okay, so here means the total number of electron is 10 to the power 22, but for any device application by any semiconductor, either it will be pure case, means intrinsic case, or doped case, it will be nearly reached to 10 to the power 15 per centimeter cube. Okay, so there are devices which are heavily doped where the carrier concentration may be, suppose if you are even heavily doped to intrinsic semiconductor to get a very high conductivity. So even that time also, even you reach only up to 10 to the power 18 to 10 to the power 19 per centimeter cube. So in a band, as I said, there are typically 10 to the power 22 electrons, and the carriers which are available for very highly doped semiconductors for device application is around 10 to the power 19 only. Okay, so there are huge difference, billion to trillion, trillion to other next term. So there are very huge difference. Okay, so what I want to say, this complete bands Why this curve? Because this curve contain all the available bands. 1, 2, 3, 4, if you are characterized like that. So these bands are available for all the available electron inside the material or all the available charge particle inside the material. But those electrons which will take the participation in conduction or which will be responsible for conduction, their numbers are very low, and that can be accumulated nearly in few bands, and that bands are found nearly to maxima of valence band region. Means suppose this region is enough to give the accommodation of those carrier electrons or those carrier which are available or which are responsible for conduction inside the material. So these regions are enough to provide the accommodation for those free charge carriers in valence band, and these regions nearly to bottom of conduction band in conduction band are sufficient to provide the accommodation for free charge carriers. Okay. Others are not useful for any device application. What you can conclude on the basis of, maybe your band structure is like that, but near to the bottom of conduction band and top of the valence band, your band will be always parabolic in shape. Okay, and near to this region, all the characteristics of device will be governed by those electrons which are accumulated near to this region. Means near to maxima of valence band and bottom of conduction band. Okay, and this region will be always looks like a parabola. That's why we will always consider the parabolic approximation of band structure in optoelectronic application. Why? Because these regions, these parabolic, nearly parabolic regions are only responsible for optoelectronic device application. Means whatever the electrons or holes are present near this region will only conduct inside the material. Due to their conduction, the conductivity will arise, and due to that the mobility will arise. Means you can calculate the conductivity of material due to transition from this region to this region. The optical property will govern, not from here to here or here to here. From here to here or here to here only the optical property will govern. Okay, that's why the space near to bottom of conduction band and the top of valence band is very important, and that region will be always found as a parabolic in shape. That's why the parabolic approximation of band structure will be considered. Okay, because all the free charge carriers are accumulated near the band edge. This thing is also known as band edge. So the same thing is written here, the parabolic approximation of band. Therefore, in all the device, when you want to analyze the device characteristics, means what is their what is the conductivity, what is the optical response. Normally it is sufficient if you know the EK variation near the bottom of conduction band and top of the valence band, because almost all carriers, the holes and electrons are accumulated near the bottom and top of their respective bands. The variation of E is nearly parabolic there, and so we use the parabolic approximation of band. Okay. So in parabolic approximation, suppose this is the your conduction band, this is your valence band, and this bottom energy is characterized by EC, and this is the region where your parabolic approximation hold. Okay. So suppose the electron is here. If that electron is here, its energy is EC. Suppose the electron is little bit up. So what will be the energy of that electron, or what is the energy of electron if that exists this energy level? So just I told that electron nearly to in this region, the electrons are able to free inside the material, means that electron are considered as a free particle. So what is the value? This value is EC. Then if electron is here, okay, so what will its energy? So that electron is considered as a free particle, means it will have the tendency of motion. If that electron are doing any kind of motion, means that electron have a kinetic energy, and kinetic energy will be denoted by P square by 2m, and that is the quantum mechanical particle. So in quantum mechanics, the momentum P is designated as h cross k. So P square is how much? H cross square k square. So you here EC plus, if the electron is here, due to its kinetic energy. So just you have to add the term EC plus h cross square k square upon 2 mc, where mc is the mass of electron in the conduction band. Okay, where mc is the effective mass of the electron in conduction band. Okay, so here the energy, and if the electron is here, means it's have some kinetic energy. So add the value of that kinetic energy in this bottom energy EC, you will get the value of energy of that particular electron. E is equal to EC plus h cross square k square upon 2 mc, where mc is the effective mass of electron in conduction band. Okay, so why this term will consider? This term is only considered on the basis of parabolic approximation of band. And why this parabolic approximation? Because near to bottom of conduction band and top of the valence band, the available charge carriers are only responsible for take the participation in conduction. Those electrons are available charge particle will only take the participation in any type of conduction inside the material. So near the region of valence band and conduction band, the shape of the band will be nearly parabolic. Okay, that's why the parabolic, for calculating the conductivity or for calculating the effective mass, we consider the parabolic approximation of both. Both means conduction band and valence band. Okay. Similarly, for valence band region. This is the topmost energy in valence band and designated as EV. Suppose obviously in the valence band, if any charge particle, that charge particle is considered, if any moving charge particle, that charge particle is considered as hole. So if any hole is characterized by this level, so this hole have even less energy than this hole. Okay. So that's why the whole of this energy E is equal to EV minus H cross square K square upon 2mb. Why this H cross K square upon 2mb? The similar approximation like electron, the hole will, you can also consider the hole as a free charge particle. Okay, and that holes are able to move inside the material. So if they are able to move, they definitely have some kinetic energy. So kinetic energy is expression is P square by 2m. Just convert this P in quantum mechanics. P is what? P is equal to H cross K. Put the value of H cross K here. What you will get? H cross square K square upon 2m. So just divide, subtract that energy from topmost energy of valence band level. You will get the energy of holes in that particular energy level. Okay. So we can treat the carrier as free particle, then kinetic energy of free particle is P square by 2n. Then put the P as a H cross K, you will get the desired result. See here, this is the actual diagram, calculated, real picture. Not real, what is the sense of real? Actually, it is the calculated band structure of very famous semiconducting material known named gallium arsenide. Okay, so see, this region, this whole region is valence band and this whole region is conduction band. So near to band edge means bottom of conduction band and top of valence band. This bands looks like a parabola. Parabola. Okay, that's why parabolic approximation. So if you see the whole band, it will not go parabolically. If you see the whole band, all the band, it will not looks like a parabola. But if you see only the bottom of the conduction band and the top of the valence band, the parabolic approximation is very good approximation. Means you can easily see that. This approximation is used in deriving the density of a state also. Okay. Why we are discussing all this? Why? What is our main motto? I want to calculate the density, available number of state in the range k to k plus dk. But for calculation of this thing, means available number of state or density of state, you have to know all these things. What is the parabolic approximation? What is the band structure? What is the top of valence band? What is the bottom of conduction band? What is the effective mass? Okay. So generally the effective mass will be characterized as or designated as m star and its value is 1 upon 1 plus h cross square d2e by dk2. Okay. So if you are calculating the effective mass of electron, that will be considered as Me star and denoted by characterized as like that. If you are calculating effective mass of hole, that will be designated as MH star, and the same procedure you have to adopt 1 upon h cross square d2e by dk2. What is this d2e by dk2? That is a fitting, or you are take the variation of energy value two times. If you are taking the energy value variation with respect to k two times, okay, and once you fit the parabolically these value, you will get the effective mass. Now some calculated effective mass, and on the basis of effective mass you can calculate the mobility. So if the effective mass is low, your mobility will high. This is the normal physics rule. If the mass of any particle is less, it can travel faster. Okay. So suppose there are some primarily used semiconductor material like silicon, germanium, gallium arsenide, indium phosphide, gallium phosphide, and based on this formula and some calculated band structure like that, you can calculate the effective mass of holes and electrons. For calculating the effective mass of hole, you have to fit the parabolic approximation over the top of valence band near to very small region, very small variation of energy. Okay, so that's then only the parabolic approximation will be hold. Okay, so based on our fitting and this calculation, means if you want to calculate the effective mass of hole, you have to fit the parabolic approximation over very few energy value for top of valence band. And if you want to calculate the effective mass of electron, you have to fit the parabolic approximation over this band, means bottom of conduction band near to very few k points or very few energy value. Okay, then you will get the, you have to fit, this is the constant h cross square, Planck constant. H cross is what? H upon 2 pi. So just put the value here, you will get the effective mass of hole and electron for corresponding material. It will be vary for different material because every different material will have the different band structure. Okay. So based on all these things, some effective mass value for some primarily used semiconductor material like silicon, germanium, gallium arsenide, indium phosphide and gallium phosphide is given here. So see, silicon have effective mass of electron is around 0.98, hole 0.49, and based on these effective mass, you can calculate the mobility. So once the effective mass is lower, the mobility is lower. See, the effective mass of hole is less than the effective mass of electron. So mobility of even hole is higher than the mobility of electron. So that silicon is considered as a good p-type semiconductor. Good p-type semiconductor. Why? Because mobility of hole is lower. Okay. So if you want where the p-type semiconductor, good conductive p-type semiconductor is required, you can use a silicon. So in germanium, see the effective mass of electron is very less, 0.08. Hole is little bit higher than this electron effective mass in germanium. So correspondingly, what you are getting? You are getting the huge value of mobility for electron comparison to holes. Similarly, 0.07. See, there is only 0.01 difference in germanium and gallium arsenide effective mass. But see the difference of mobility of electron. Here the mobility is 3900, but here the mobility is 8500. Okay. So indium phosphide same 4600. Mobility not only depend on the effective mass, there are some other terms also. That's why even the effective mass is same. Here the mobility of indium phosphide is less than the comparison to gallium arsenide, and 0.64 effective mass. So here the mobility is 150. So these are some calculated value based on the calculated band structure for silicon, germanium, gallium arsenide, indium phosphide and gallium phosphide. Okay, so you can draw your conclusion. Okay. So semiconductor material like silicon, germanium, gallium arsenide, indium phosphide, gallium phosphide, etc. are widely used optoelectronics semiconducting material. So the effective masses are, that's why the effective masses are given here. There are something called light holes or heavy holes, means those semiconductor having the lighter weight of holes is called light hole material, and those semiconductor material having the little bit higher effective mass of hole is considered as heavy holes. But here we are mainly considering the heavy hole, as I do not wish to introduce light holes because light hole have some typical nature. Light hole means good p-type semiconductor. But generally all the semiconductor, widely used semiconductors are n-type semiconductor, and n-type means they are good for, and they have a lighter electrons, means effective mass of electron is less comparison to holes. So that's why the heavy hole material are generally found and normally. So note that the smaller the effective mass, the larger the mobility. So you can also see that the mobility of electron is much more compared to the mobility of hole. So the band structure tell us the effective mass and also the corresponding mobility. And based on all these, effective mass, mobility, energy band gap, okay, if your concept is clear about all these things, you can easily calculate the density of state. So for today it is enough. In next video lecture, we will calculate the density of state. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.